It is my pleasure to present the speaker today. Dr. Mark Utting is visiting us from University of Waikato in New Zealand and is going to be talking about model-based testing, in particular tools approach, a practical approach, which is something that I think is really timely because we are looking at it extensively for multiple projects. I know we have two of the offices online, so Kirkland and Boulder, hi to you guys. And what I'm going to ask everybody to do is hold the questions till the end, unless there is a clarifying issue, because there is a lot of material, and then at the end we will just open it up for questions, and we'll also take questions from the remote offices as well. So please feel free to jump in once we open it up. So with that, Dr. Utting.
Thank you very much. So I just thought I'd start with a brief geography lesson to say where I come from. And mention that this is not just all work that I've done by myself. I've had a very close collaboration over the last 6 or 7 years with Professor Bruno Lejar and a group in France that have now formed a company. So some of the things I'm talking about have been done with them. So I got a surprise when I looked at this, how far California is from New Zealand. It was hard to fit them both on the map together. It's 12 hours flight. So I'm from the North Island of New Zealand. In Hamilton there, that's a Google shot of Hamilton, and this is the university, and I'm in the computer science department there. So the structure of the talk, there's 4 main parts, things that I want to talk about, plus conclusions. I'm going to start talking about an overview of model-based testing, and I think a lot of you already have heard quite a lot about model-based testing, so I'll go fairly fast through that. Just to give a brief introduction. Then I want to talk about black box versus white box, not black box testing, because we're always doing black box testing from requirements, but black box models, white box models, which I think is just an interesting distinction. And the main part of the talk is to give 2 examples, one using a black box model, using a tool, open source tool that I've developed in the last year, with the models are written in Java, doing unit testing. And another one, a white box model, using a commercial tool, doing system testing. And this one's offline, that one's online. So I've kind of tried to make things as different as possible between the 2 examples, so that you can see a bit of a spectrum of the model-based testing approaches and tools that are possible. Okay, so what is model-based testing? Well, the definition I like, perhaps because I thought of it, I would say the automation of test design. So we hear a lot about automation of testing. That usually means the automation of test execution. Okay, I want to push that further. I want to try and automate the design of the tests. So I'm assuming that the execution probably is automated, but I want to go further and see if we can actually execute and automate the design. And so we do that by generating tests automatically, have some tool, from a model of the system under test. There are different definitions of model-based testing. This is quite a strong definition that I'm taking here, where the model is actually a model of the system that we're testing. And so let's contrast this with traditional approach to testing. We'd start with the requirements, and someone manually would read those, understand those requirements, and develop a whole bunch of test cases. Okay? In contrast, in model-based testing, we are trying to just develop a model from the requirements, a model of part of the behavior of the system, not the complete behavior. It's very important when you're doing model-based testing to try and miss out some of the details, to try and abstract and come up with a simple model or several simple models that touch on different aspects. So there's quite a skill in doing this and coming up with the right level of model. It's not just something that every programmer can do. It requires the ability to do abstraction. But once we've got that model, then we can have some tool which will automate this part here. And so the hope is that overall we do less work, because the work of writing a model is hopefully less than the work of writing all the test cases. I'll talk more about that later on. just to put this in perspective, you may have seen this diagram before. It's sort of a three-dimensional taxonomy of the space of testing. So we've got code-based testing here, where we're driving our test design from the code itself. What we're doing in model-based testing is black box testing, developing our tests from the requirements. And it's mostly aimed at testing the functionality, a little bit testing the robustness. There hasn't been a lot of work done on performance testing, for example, using models. There is some on that, but it's not quite mainstream yet. But on the other scale, model-based testing can be used for unit testing. We'll see an example of that shortly, or anything up to system testing, and we'll see an example of that as well. So I thought I'd introduce it by example. This is an example that comes from France. It's a system over there called Qui-Donc, and that literally means who's there. And this is a service of France Telecom where you ring up a number, you type in a phone number, and it'll tell you who owns that phone number, their name and address. Is there a service like that in the US? Google, okay. Yeah, in some countries it's not allowed, but it's interesting, in France it's actually a public service of France Telecom. So it's kind of the inverse mapping of the white pages. So here's a typical use case. We dial the number, and we hear a message saying something like welcome. This is all in French, of course. I've translated it for you. Press the star button so that it knows if you've got a touch phone. And if it hears the star button, we press the star button, and we hear another thing saying, please enter a 10-digit number followed by the hash key, pound key. And then we enter a number, and if it's a number that's in the white pages, then we'll hear the person's name, and we go into another options of hearing their address, spelling their name, finding out their credit card number, you know, all those kinds of things. I exaggerate a little. So we might listen to his address and then hang up. So that'd be a typical use case. If we wanted to write a model of this, we could come up with a fairly simple finite state machine model. And here's a really simple one. So you're all familiar with finite state machines, I guess. So if we just go through the use case here, we'll see that starting in the offline, if we dial the number, then we expect to hear the welcome message. And that takes us into a state which is waiting for a star to be pressed. If we press the star button, then we'll hear the please enter a number message. And we'll be in this state where we can enter different kinds of numbers. If we happen to enter a number that is in the database, then we'll hear the person's name and be able to then go into a state where we can get the spelling of his name, the address, etc. Hang up at any time, wrong numbers, all kinds of things. So that's a really simple model that is actually quite a lot simpler than the real system, because the real system has timeouts. On each of these states, it has 3 10-second timeouts, I think. So eventually after that, 3 timeouts, it'll go and hang up. But as a first approximation, that's a nice, simple model. So how could we generate tests from that? Well, it's fairly obvious. We could just take a walk through the system. And the first thing we might like to do is let's just take a random walk. So I'm going to talk about a few different test generation algorithms. A random walk, we'll just say, at each node that we get to, each state, let's choose a random path out of it. So we start off, there's only one to choose from. And then we randomly choose the star one. Randomly choose a number that doesn't happen to be in the database. So we get a, sorry, I don't know that number message. Choose a number that is in there. And then hang up. And we're aiming to produce a test of length 10. So we're still carrying on, dialing up again, happening to take the same route. This time we type in the fire brigade's number, and randomly, you don't always get very good coverage with random, right? Because it happened to take sort of the same choice twice there and twice here. Perhaps it would have been smarter to explore some of the other routes. So random is pretty dumb, but it's extremely simple to implement. It's like 2 or 3 lines of code to go through and generate a random algorithm. And it has some nice properties that eventually a random generation will cover every path, every subsequence. So it's getting more and more sophisticated coverage, if you like, the longer you let it run. So you can just let it run for several hours if you want. So that's a really dumb algorithm, but surprisingly useful in practice. Here's a more sophisticated one. The Chinese postman is the problem of you have to walk down every road to deliver all the letters. And so here we want to make sure that every transition has been visited. And we'd like to do that in the minimum amount of time. So that's what the Chinese postman algorithm does. And if we do the Chinese postman on this, it'll come up with one tour, which is minimal length, tries to avoid doing anything twice. It actually has to traverse this line 3 times because there are 3 ways of getting back to that state. But apart from that, it does a pretty good job of avoiding duplication. So that's a nice algorithm to do. We could say, well, we want to go a bit more than that. We want to test, for this particular state, we want to test the interactions between the ways you can get into the state and the ways you can get out of it. So that would be all transition pairs. So for each input, we'd try and have some tests that try all the different outgoing transitions. And same for the other input, would try the 3 transitions. So for each state, you're kind of getting an n squared number of tests. But so it's roughly n squared in complexity. But still, it starts to test the interactions between operations. And this is one that I quite like. This is one that I first heard described by Harry Robinson, who, when he was at Microsoft, or maybe at Google. And let's say we've got a use case, and that's the dark black line here. And we know that that's going to be something that people will often do. And so we want to test some minor variations on that. So first of all, we'll obviously test the use case itself. But then we take all of the sort of minimum cost permutations or mutations of that path. And so, for example, instead of taking the recommended line there, we might take the alternative one. Instead of taking this one here first, we go around back that loop, and so on. So we can choose all the alternative paths and get some kind of user-directed testing. Because this one here, unlike the first 3 algorithms there, are all completely automatic, sort of blind algorithms. You just push a button, they'll go and do it. This one here is actually being driven by a use case. So a test engineer has an opportunity to say, hey, this is a really important thing. Test this thoroughly. So it gives you a bit of user input on what you want tested. So those are some examples of how we might generate some tests. Then, of course, we want to actually execute these tests. There's 2 ways of doing this, offline or online. And I guess the distinction's pretty obvious. In offline, we can generate the tests and store it in a file as just a sequence of commands or as code. And so we can then take that file and execute it on a different machine, execute it later, put it into our test management suite and run regression tests every night. So that the generation and the execution are separate. Whereas in online testing, the tests are actually executed as they're being generated. So if you think about the graph example, we take one transition of the graph, we send that off to the system under test, wait for the response to come back, check if it's correct, and then generate the next step. So it's very tightly coupled. And obviously that's good, or necessary really, if you're testing a non-deterministic system under test. Because when you send a stimulus, you're not sure exactly which response it's going to come back with, or it may generate spontaneous responses. And so in that case, probably your generation algorithm wants to be able to react to those, to that non-determinism and change the path that it's taking. And it's also good for things like online testing, overnight testing. You can just say, well, keep on testing until I come in the morning. And so it can be generating them dynamically as you're going. So those are the 2 basic distinctions of the way we can execute. And again, we'll see one example. The first example I'm going to do is going to be online, and the second one will be offline. So what are the benefits of model-based testing? Well, the obvious one you think of is this is going to save me time, because hopefully the time taken to write the model, if it's a nice abstract model, fairly small, simpler than the system you're actually testing, hopefully that'll be less than the time taken to design test by hand. And of course, if we have a automated generation, then the generated tests should be executable, and when we execute them, they should have an oracle in them which actually tells us whether the test passes or fails. So we kind of get all that for free. The only painful part is designing the model. It's the theory. In practice, we've done some industry case studies. My colleagues in France particularly have done quite a lot of work with industry, and in some cases they found there's a sort of 30% saving in time. So the time of doing the manual test is 30% longer than the time of writing the model. In other cases that I've seen, it's actually roughly the same. So it's not always clear whether you're going to get a win in terms of cost savings and time. So that can be a benefit, sometimes, other times not. The other benefit you get is systematic testing. If we are sort of using a systematic algorithm to cover our model, then we can be sure of covering every action, every transition, etc. So maybe if you're manually designing tests, you'd forget some of the cases, so that can be good. And by changing the test generation parameters, we can control how many tests we get. But this next one is a surprising, perhaps, benefit people don't think of when they first start doing model-based testing, is that just the act of formalizing the requirements and changing them into model raises questions like, okay, we're in the state here. What does happen when you press the star key in this state? The requirements don't say anything about it. And so we have to go back to the users or designers and clarify that. And those kind of things happen virtually every time you write a model. And that is actually, I read a really interesting report from Microsoft talking about this. When they started using model-based testing a few years ago, one of the things they noticed was that testers were preventing a lot of errors. Because as they were modeling, they were detecting these ambiguities in the requirements, feeding them back into the design process, and that was probably preventing errors from ever happening. Okay? But the interesting thing, the sociological thing was, the testers didn't get any reward for that. In fact, there was no way of measuring it. They can measure the errors that have been created and then found, but there's no way of measuring errors that have been prevented. And so there was no sort of reward mechanism for it, which is an interesting observation. So that can be a surprising benefit. This is my favorite one, and one I think is most significant, that if we have evolving requirements, which almost always we do, with model-based testing, you can just change the model, update it a little bit, and then push the regenerate and re-execute the tests button. Okay, and hopefully that's automatic. And so it's probably a lot less work changing the model than it is to go and maintain a large set of manually designed tests. And with some tools, when you change the model, you can actually regenerate the tests and run just the ones that have changed. So you don't need to run your whole test suite again. So that can save you execution time as well. And we can sometimes also get the traceability automated. So if we annotate our model with requirements IDs, we say, requirement 32.5 is related to this part of the model here, then the tools can actually track that and can tell us exactly which tests are testing that requirement. So because the tests are generated automatically, you can kind of keep track of that traceability. So those are some of the benefits. The main negative is the modeling. The time taken to do the modeling, the expertise required. Sometimes it's like a programming job, but it's a bit different to that because you also have to be raising the abstraction level. Okay, so let's talk about black box and white box models. So imagine now that someone has taken this big requirements document, they've understood it, abstracted, they've written a model, and now they're giving us, the model to generate some tests from. So just put yourself in the place of a test generation algorithm, and we want to see what's the difference between being given a black box model and a white box model. Well, obviously a black box model is black, right? That's the obvious difference. But a black box model, we can't see inside it. All we can see is that there are these 3 actions we can perform. We can reset it, and we get this view of telling us what state it's in. That's all it's going to tell us about the internals. And so if we want to start exploring or generating tests from here, all we know initially is that we're in state 0. And so let's try pressing the A button. And the state changed to 3. So that means if we take this transition here, this part is going to be state 3. Now let's try pressing the B button. State 19. So that means this one is state 19. And if we press C, we get state 20. This is starting to look like a long job. We don't know how big this model is. It could be huge. Let's try pressing C again. State 0. Right. We've gone back to the initial state. So this transition here actually links up back to our initial state. So we're gradually exploring the model. We could be actually generating tests as we're doing this if we're just following a random path. And as we do, we're finding out more about the internals of the model, the behavior of the model. But we can't see it up front. So I suppose I could have done this yesterday because it's my first weekend I'd stayed in San Francisco and I wanted to explore the city a bit. So this would be a little bit like me going outside my hotel, catching the first bus or train that comes along, staying on for 10 minutes or until I see another connection with another bus, getting off there, choosing that bus, just randomly swapping buses every 10 minutes or 5 minutes. I guess I'd see a lot of San Francisco, but it wouldn't be very directed, and I probably wouldn't get to the places that I actually did get to. As you can imagine, my strategy was a little smarter, less random than that. My strategy was to actually look at the map and figure out, oh yes, I'd like to go there and there and there. In actual fact, it didn't help me much because I walked out of the hotel and started walking east and realized after a few kilometers that I was actually going west because the sun was in the wrong side of the sky. But coming from the southern hemisphere, you see. But I eventually got that sorted out. So here's a white box model. And the obvious difference is it tells us, we can just see the model there. We can see, oh, this is quite a small model. It's quite simple. And we've got the same controls, same buttons, but we can actually see exactly where we are. We can plan in advance. OK, let's take an A transition there. Oh, yes, better take a B. Let's go C. Oh, let's take a B transition. We're in a terminal state. So we need to do a reset. So we can kind of see all that. And if we want to plan ahead, plan a path to make sure we go and cover a loop, or Chinese postman, all transitions, we can easily do that. So which would you prefer? Well, obviously white box, right? There's more information. You've got to be able to do better with more information. But I guess my point is there are some trade-offs. And the reality is that finite state machines just aren't good enough. Finite state machines are too simple. If you start modeling a real system, you rapidly find out that your system's got a few hundred states or a few thousand states, maybe billions, and you just can't draw that. And too many transitions. So they become too large. So in practice, when we're doing modeling, we need more expressive notations. And one common, widely used notation is extended finite state machines, where we add state variables to our model to store some data. The data that's kind of a little bit independent of which state we're in. It's useful for several states. And then our transitions become significantly more complex. They can perhaps take parameters. They can have guards to say whether this transition is allowed or not. So sometimes when you reach a state, the transition's enabled, other times it isn't. And when you do take the transition, then it can execute an action which can update the state variables. So we now got sort of a programming language, more than just a state machine. So for example, if I was taking the bus, I might say, oh, well, how far am I taking the bus? That's kind of a parameter. And I'm only going to take this bus if it's going more than 5 miles, sorry. And if it does, it's going to cost me $3 or something. add $3 to my cost. So then we can start having a more complex model, more dynamic behavior. So the question is, what language are these guards and actions written in? And this is where we get to the one of the key slides of this talk, which is the difference between black models and white models. And one of the things I think is important is that if you're writing a white model where everything's kind of open, you want to be able to, and you're going to have a tool that's going to generate tests from it, the tool has to understand the semantics of the model. So it has to understand not just the idea of states and transitions, but it also has to understand the actual language that's used for the guards and the actions. So that kind of means you need a declarative language with simple semantics, clean semantics, to describe your actions. For example, we could use OCL or something like that to describe the behavior of the actions, which means that it makes it easy for a tool to analyze, if I take this transition, I know what's going to happen. Whereas in a black box model, the tool can't see that. All it can do is decide whether to execute it or not. And so we've got freedom to use any language we want. We can, so long as the language is executable, that's all that matters. It doesn't have to be, the semantics doesn't matter, so long as it's executable. So that means we can write our actions in a familiar notation, any programming language you like, regardless how horrible. It's got pointers, recursion, loops, pointers, I mentioned that already, and object-oriented dynamic dispatch, that's a real pain to reason about. All those kind of things would make it really hard for a tool to figure out exactly what's going to happen when we execute this program. But it still is executable. So the obvious trade-off is that with a white box model, we can see the model in advance, we can do some planning, say, oh yes, I want to follow that path there, and sort of, we know that guards are going to be, we can choose some data which will make the guards true. Whereas with the black box one, we can't do that, we just have to discover the model by exploration. And so for test generation with black box, you're a bit limited. You can do some simple things like random walks, use cases and things like that, but fairly simple algorithms because you don't know the whole model in advance. As you get to discover more of the model, you can do more sophisticated things. Whereas in white box, you can do all those simple things, but you can also have some extremely sophisticated symbolic reasoning, saying, I want to reach that state over there, find me a path that will satisfy all the constraints and get to that state. So it's a lot more demanding on the tools, but more powerful. So that's one of the key points of the talk. Now, I want to go through two examples. The first one is using black box models, using ModelJUnit, which is a tool that I've written in Java. So the goal of this tool is to be the simplest model-based testing tool you could possibly have for a programmer, because I'm a programmer and my students are programmers. So if you were not a programmer and you wanted sort of a drag and drop, draw the graph on the screen kind of tool, probably you'd end up with a different kind of tool. But for me, I want to write the models in Java, for example. And so this is the kind of tool that I ended up with. So we can write our models using the full power of Java. We can use inheritance to factor out common parts of the model. We can use loops. We can use extra methods. We can use object orientation, dynamic dispatch, all these kind of things that we do for good software engineering. We can do them on our models. So our models can be really expressive, but still quite concise. ModelJUnit is kind of aimed at unit testing. Could be used for system testing as well, but I've made sure that it's well integrated with JUnit so that it works well there. And it just provides a few simple test generation algorithms, a purely random walk, a greedy walk, which tries to prefer fresh paths over used ones, all round trips, and a few other things like that. So it's quite a simple tool. So let's have a look. Imagine now that we want to test one of the standard Java data structures, a set of elements. And the first thing we have to do is realize that this has got an infinite number of states, and we could test all day. We need to make some serious abstractions to reduce the size of the system. And so I've decided, major abstraction, let's just test maximum of 2 elements. Choose two elements, and that'll be enough to test our set. Very simplifying assumption. So we end up with quite a small model like this. We say, okay, we start off in the empty state. If we add string 1, we'll have a set containing just that. We add string 2, we'll have the full set with both elements in it. If we delete S1, we'll be just have this one left. Delete S2, back to empty, and so on. So that's very straightforward to understand. In fact, if you think about it a little, you realize there's a few transitions missing. We should add these ones. If it's full and we keep on doing adds, it doesn't change. That's sort of part of the setness of it. And so same if it's empty and we do deletes and so on. So this is an extremely simple model, 4 states, 4 actions, 16 transitions. You could draw that out with a graph drawing tool. But I want to do it in Java. So how would we do that model in Java? Well, here's the code in Java. The red parts are the parts that are required by ModelJUnit. So every model must implement this interface, which has these 2 methods here. And the action annotation tells it what are the actions that are callable from each state. So these define the transitions. So a programmer who's thinking about this model will realize, well, I don't really need to model sort of the complete contents of the set. A better way of doing it is to just keep track of whether string 1 is in there or not, whether string 2 is in there or not. So 2 booleans is a nice way of modeling this. It keeps things simple. And so that is protected state because this is a black box model. We can't see the internals of the state. We don't know the internal semantics of what these methods do. We just execute them. To provide the observation, the little LED panel that shows the internal state a little bit, we can define that to be whatever we want. So we can have a different view of the state than is actually our internal protected variables. But in this case here, I'm just decided to output the 2 variables as true or false. So this is kind of a faithful representation of the internal state. You can have representations that throw lots of information away and give you a small number of states. And we need a reset operation, which just sets them both to false, and a few actions. And for example, if we add string 1, it just means setting that Boolean flag to true. If we delete string 1, it means setting it to false. So it's an extremely simple model. So that's about 10 or 11 lines of code. Those 10 or 11 lines of code define the 4 states, the 4 actions, and by executing them, the 16 transitions. So this model is kind of smaller to describe than drawing all of the things by hand. When you get to large models, you can have a relatively small Java class that actually creates large models. Well, that's not really the goal. The goal is to keep your models as fairly small as possible. So we've now written our model, this red part here. What else do we have to do? Well, the red parts are the parts that the user has to do, and the blue parts are provided by ModelJUnit. So we've written the model that's implemented that interface. ModelJUnit also provides a wrapper that sort of goes around this user's model, and it uses reflection to find all the actions. It allows you to execute actions and resets. It keeps track of a set of listeners and tells them everything that's going on. So there's several listeners that can keep track of the coverage of your testing. And most importantly, it has this hierarchy of classes to do test generation. So an abstract one to generate tests, and then several implementations with different algorithms. So the last thing we have to do as a user is write a few lines of code which will choose a test generation algorithm and pass our model to it and make it work, generate some tests. So here's that code. Choose a test generation algorithm. We're going to create a greedy tester and pass it our model. And then how many tests? Well, let's go for 150. So those 2 lines of code will use that model and generate a test sequence. Or if we wanted to, we didn't want to write those 2 lines of code, we could use a GUI and just go and click a few options, and it'll generate that code for us or generate the tests for us, either way. The idea of that is just to reduce the overhead of learning ModelJUnit. So you have to still write the model in Java, but then you can just use it and experiment with different test generation things. So if we do that, we'll get a whole sequence of 150 transitions. Here they're just printed out as triples. So we can see it starts off from the empty state, adds string 2 randomly, gets into the state false true, and then from there adds string 1, so now it's full, deletes string 1, goes back to that state, deletes string 2, so it's empty again, deletes string 2 again, and stays empty, and so on, carries on. And ModelJUnit will also tell us that, okay, after 8 transitions, you've actually covered 50% of your model, 50% of the transitions. After 30-something transitions, you've got 75%, and you'll get 100% transition coverage after 116, which obviously isn't very optimal. That's just the greedy algorithm still isn't an optimal way of covering things as fast as possible. There's better ways of doing it. So that has created a model and allowed us to generate tests from it. We could use those for offline testing. We could just take that output script and write some separate program which goes through and executes it. But we can also do online testing, so let's do that. To do online testing, one way of doing it is to add some glue code, some connection code that connects our model to an implementation. I'm just going to test HashSet there. Well, I don't expect to find any errors in that, but let's just use that as an example. And so every time we do an action in the model, like adding a string, we're setting one of the model variables to true. We'll also do a corresponding action on the system under test. Okay, adding a particular string, string 1 there, adding the empty string there, and so on. Same for delete. So you can imagine the idea of model-based testing is that the model is evolving and changing state, and in parallel, the system under test is changing state, a more complicated state. And we need to check that the two are in sync. So something missing from this would execute okay, and it would kind of test the set, but we're not getting much feedback. There's not much oracle here. Oracle as in the wise woman who sits on top of the hill and tells you whether you're doing the right or wrong thing. We need an oracle to tell us whether the tests are passing, whether the HashSet is doing the correct thing. So let's add an oracle as well. And the way I usually do that is just for each method to call a checking routine after it's changed the model state and the system under test. And now this routine here will check that the two agree. And here's the code, some example code for that. To check the two agree, well, we could calculate the size of our model set, which would be 0, 1, or 2, and check that that's the same as the size method of the system under test. We can check that the contains thing works correctly and agrees with our flags. We could go a bit further and check the isEmpty method, check the equals method, and so on. You can add as much sort of consistency checking as you want, depending on what you want to test. So there's the adapter code or glue code that links our model to the system. Right. Imagine now that HashSet had a bug, and say if you try and remove an empty string, something goes wrong, then this is what would happen when we run it. We'd actually run it, we'd see a few transitions working correctly, and we get an error report like this. Failure in action, deleting string 2 from the state, false true. And in this case, maybe a null pointer exception. It's just, this didn't really happen, right? I don't want to be sued by Sun here. This is just an imaginary example. And some sort of stack trace so you can track it down and find out what caused the error. So in reality, I've run this on HashSet, and it didn't detect any bugs. But it still leaves me wondering, how good is this test set that I've generated? And so I thought I'd answer that a different way, introduce another tool This is a tool that has kind of come out of a university that I'm at, but it's also from a commercial company and that split off from our university called Real2. And they've released that as, this is open source just a few weeks ago. And it tries to measure the goodness of your JUnit test suite. And it does that by taking the actual class that you're testing and mutating it. It does a whole lot of different mutations. And for each mutation, it runs your JUnit tests and sees if they detect the mutation. And if they do, that's good. That part of the code is tested fairly well. If it doesn't, then maybe your JUnit tests aren't good enough. So we can measure the percentage of mutations covered. If 0% of the mutations are detected by your unit test, you probably haven't got any unit tests. So that's a bad sign. If you get 50% of the mutations covered, probably your unit tests are pretty inadequate, because 50% of the changes to the code aren't being detected. So there could be a lot of bugs in there that the unit tests won't pick up. If you're getting sort of 80 to 95%, then you've got really good unit tests. And 100% is ideal in theory, but sometimes difficult to achieve because of the way the code's structured. So it just gives a useful measure of how thorough your unit tests are. No, this is not measuring code coverage at all. This is measuring the percentage of mutations that are covered. So 100% means that every single mutation of your class is being detected by the tests. This is probably correlated with code coverage, but it's not the same thing. It's probably more demanding than code coverage in many cases. So I ran Jumble on the test that we've generated. So I actually wrote my own little toy implementation of set of strings. It's sort of 100 lines of code, I suppose, just using an array. And run Jumble with a -r flag, which does a bit more mutations than normal. And I had the grey code, to check the isEmpty and equals methods. And I also added some code to check the result of the add and remove methods. And so Jumble finds 25 mutations in my code. And comes back, and each dot is a mutation that passed, as in the unit test detected it. And the other ones here, the two failure messages, are mutations that weren't detected. And so I come back with a score of 92%, which is pretty good. These two turn out to be, this is the iterator through the set, which is just, I return the iterator through the underlying array list. And my tests didn't actually call the iterator at all. So it's kind of pointing out to me that, hey, you forgot to test the iterator. And this one down here is some complicated if-then-else case inside the loop of the equals method. I'm not sure why that's not being covered by these tests. I'd have to investigate that further. So it gives me a bit of feedback that, yes, the generated test, that 150 sequence, is pretty good. It's covering the code, covering the implementation quite nicely. But there's a bit of room for improvement. So let's look at a white box example. So the example notation I'm going to use here is UML. And we'll use a class diagram to give the overall structure of our system under test, and an object diagram for an initial state scenario to do the testing from, some state machines to specify the behavior of some of the classes, and some OCL for the methods in the other classes. And the example tool will be a commercial tool that's been in development for about 10 years, but in commercial production since 2003. And the latest version uses quite a sophisticated automatic reasoning engine from prover.com, which is kind of like a really powerful automatic theorem prover to actually analyze the model and generate tests. So how does model-based testing work with this tool? Well, you model in UML, and we use Boolean together to do that, and then export the tests from that and go into the Lerios test designer, where you can select your test generation and generate some tests, and then after you generate tests there, you export them to some executable language, maybe JUnit script code, or maybe Quick Test Professional, something like that, or various other testing languages. And then, of course, you execute those. So let's go briefly through that. I'm going to use a library system as an example with a sort of web-based interface. So each subscriber logs onto a terminal, does some loans and things like that, and will generate JUnit tests. And these can either execute by connecting directly to the library API or via Internet Explorer using a wattage library, which clicks on links inside Internet Explorer. So here's our model. The class diagram is a simplified class diagram of the real system because we can throw away a lot of detail, but it still has things like books, copies, subscribers. This is the main system we're going to test, and the idea of a session. So each browser starts up an individual session. And a session has a whole lot of actions it can do. We need to specify what each of these actions does, and so does the main system, which is the server. And as well as that class diagram, we'll now instantiate that class diagram to an object diagram to give us some test data. So here we'll say we've got one client, one server, two clients, two sessions in other words, two books, it's not a very big library, two copies, one copy object doesn't actually belong to a book yet, and two subscribers, one of who kind of is subscribed and the other one is disconnected, not connected yet. So that gives us some data to generate tests with. For the server, it's in different states, so it's convenient to use a state machine to model the server. And the library can be either open or closed. You can switch between those at the beginning and end of each day. And you can also take it offline to do some admin work like changing the date and things like that. So it's a very simple state machine. These transitions here, this is an event open, or say open. And then as well as an action here, there can be a guard. In this case here, day start activity. We need to define that. Rather than defining it directly in the diagram, we just do it on a separate page. And so, for example, the day start activity is just incrementing today's date. Other ones have got an if-then else in them, and so on. So that's actually OCL, which is probably new to many of you, but it's not too different to a programming language. Just a bit more declarative. And we need to define the methods in the other class too, and this actually uses quite a lot of OCL. And here's just part of the code for the lending a book operation. And it's doing things like, if the person borrowing has a book whose return date is before today, then it's overdue. So the message should come back that this is a subscriber with a late book, and so on. So there's a whole lot of cases there, and that's written in OCL as well. So that model is quite sophisticated. We export that from Ball Together and load it into the test designing tool. Then we get, the test designer has a goal of trying to sort of test every transition of a state machine, every branch of an OCL if-then else. So it ends up breaking up our whole model into a whole lot of sort of test goals, test targets, and it comes up with 80 or 90 different parts of the model that it thinks should be tested. And here's one of them, which comes from the lend book operation. And this is OCL again, and it's pretty complicated to read, but there's some various things in here. When you get to read it, you can see that, okay, for this test, to be able to generate this test, we have to satisfy these conditions. So we have to be at the right node, the right state in our state machine, and we have to have all the right data set up. So the system has to be ready, there has to be a valid subscriber, a whole lot of error conditions have to be okay. The subscriber can't be finishing his subscription before the book will be due back. And this last one here says that the subscriber mustn't have an overdue book. So there's a whole lot of conditions there, and if we get that, we expect to get this message saying that they've got an overdue book, so they shouldn't be allowed to loan the book. So generating a test for that is actually quite challenging, because the test generation's got to find a path through the state machine to get to some state where it's possible to do this test, and set up all the data to make sure we've got a subscriber subscribed and the right kind of book, and that they've got another book out on loan, which is overdue, all that kind of thing. There's nothing explicitly telling it how to do that. We're just relying on the symbolic execution engine to find a path that satisfies all these conditions. Okay? So this is one of the most important ones. It's got to have an overdue book, this person. And so the test generator has to actually search for some sequence of operations that satisfies all of these constraints, and some suitable data that will satisfy the conditions. So if we run the test generation, then in a minute or two, it satisfies about 80 or 90% of the test targets. And in this case here, it generates this sequence of operations to satisfy this case of lending a book. You see it's got about 9 or 10 things it has to do before it can actually call the lend book operation. So it's generated quite a long sequence, setup sequence. So then we can export that sequence there into Java. In fact, as I mentioned before, when we generate the test, it's actually telling us that we had 82 targets. It's managed to generate tests for 73 of them. There are 9 that are undetermined, and we could perhaps investigate those and find out whether the machine just isn't powerful enough to find that path, or whether there's a mistake in the model. So it gives you some feedback on the model, and also the requirement coverage as well. So we export all those tests into JUnit, and we might get some code like this, which is JUnit 4 code, and it's just the setup is a sequence of operations to set up all this data, and then we finally do our test, which is to lend a book. And we expect to get an exception thrown, which is a late subscriber. We could actually execute that, but to execute that, we've got to have a system under test, which is maybe running in a web browser or with an API. And so we need a little bit of adapter code, glue code, just like in the ModelJUnit case, which is going to define each of these operations and translate it into the lower level operations of the API. So again, there's some code to write there manually, but you're not writing the test, you're just writing a bit of glue code for each method. In conclusion, we've seen an example of black box models and testing from those, and white box models. My conclusion is that the black box models are simple to write because you're just doing it in a familiar language like Java, and you've got sort of complete flexibility how you define the actions. They're good for simple heuristic test generation. You can get lots of tests out of them, but there's a lot of redundancy in those tests and not a very sort of optimal test suite. And you get very weak guarantees. We can run this execution for an hour, and it might come back and say, okay, well, I couldn't reach state 32, even after trying, generating 1,000 tests. I've got no idea why, because it's not doing a deep analysis of the graph to find out why that thing isn't reachable. Whereas white box models, you can do quite smart test generation. You usually come out with a small number of tests, very carefully designed. You can kind of get guarantees like each test is the minimum length possible to test this condition. We can do look ahead, and you come back with results like state 32 has been proven to be unreachable. So that almost certainly indicates an error in your model. So there's 2 sample points on the spectrum of model-based testing showing different styles of models. This one here was offline testing, generating the tests as Java and executing them later. This one was doing online testing. And those are just 2 points. There are a whole lot of other approaches, brief commercial advertisement here, covered in the book that Bruno and I have written. And I've only described 2 notations here, but there's actually dozens of notations that have been used for model-based testing, and lots of tools, commercial tools, as well as quite a few open source ones as well. So there's more discussion of those there. So that's the end. I haven't talked about industrial applications. I could do that, but I didn't think I'd have time, and I was right. So, questions?
Hi, so when you were talking about generating the 150 tests, you put them into one big sequence. Have you, or do you know if anybody's looked at the difference between, say, 15 sequences that are 10 long versus one sequence that's 150 long, and how that can impact either coverage or defect detection
Yes.
capabilities?
Yes, that's a good question. So I didn't mention that, but I was just kind of using the default setting of that tool, which is to have a 5% probability of doing a reset. So that's why there was occasional resets. It just means on average your test sequence is going to be 20 long. But you could set that to be any percentage you want to influence the length of the tests. But the question, I have seen, I can't remember who it was, but I have seen one paper that did some research on long, complicated tests versus lots of short ones. And I think the conclusion was that the long tests are often expose more interesting errors or unexpected errors because of extra interactions. But of course the disadvantage is they're a pain to debug. If you get a failure after 1,000 operations, it's actually quite difficult to know what the cause was, as opposed to if it was just 3, it's easy to track down. And another idea from Harry Robinson, which I like but haven't implemented yet, is his beeline algorithm. Take a long sequence that's failed and then randomly cut parts out of it and see if it keeps on failing, and try and reduce it down and down and down, like sort of genetic mutation, until you get the smallest sequence that shows the same failure. That way you can try and help that debugging problem. Yeah, so there is a paper, I can't remember it off my head at the moment. Any other questions?
So it seems like one of the vulnerabilities of model-based is the state explosion. So I'm wondering what you think about how these things would scale in situations like at Google, where we have a lot of self-healing systems that use tons and tons of heuristics. It's difficult sometimes to understand what the state is, even when you've built it yourself.
Yes.
How would your solutions or your thinking relate to those kind of problems?
You're right, state explosion can be a real issue. One advantage of the black box approach is kind of, in a way, even if the state is infinite, it doesn't matter. Using random generation, you can still generate a few tests, but you're probably not getting very good coverage if you do that. You're better to try and use abstraction really strongly and come up with a fairly small model. So probably the obvious answer to state explosion is try and use abstraction to narrow down the properties that you're testing to be something that's fairly small. But that's not always easy to do or practical. So I haven't got a magic wand that I can wave and make all of the state explosions go away. Even though I am from New Zealand, but any other questions?
Kirkland or Boulder, do you have any questions? You know you can pipe in any time. Doesn't seem like it. So in that case, thank you very much for coming to Google and talking to us about model-based testing, and hope we can discuss some of the issues also offline. Thank you.
Thanks.